the idea of the optimal subpaths to not have to waste time doing every single collision. So we'll go through that example. So randomly we pick A1, and we find a path using some single source shortest path algorithm, let's say A star, and we said this is the path. So now you found all the actions for all the states in that path. You no longer have to calculate them again. So when you move on to the next state, say A2, once you find that you have a path to one of those states, say B2, you can just mark that one state as done, and you already found the policy for that. So as you can see, it does this for every single state. And once you've gone through, you have the policy. That's it. Does that make sense? Alright. So now, let's say in this example we're going to have two robots, just like the one that we just did. A robot in A1 with a goal at D4 with a policy that we just calculated. And the other robot will be a robot starting at A3 with a goal at D1 with this policy. Alright, so once we have the optimal policy, we first follow the robot's policy until there's a collision. So let's say that this is our example, right? Using the policy at the top right, what should the blue robot do? Any ideas? Move to the right, yeah. What about the red robot? Move to the right. Is there collision? No. So you just move. Alright, what about Nat? Well, they both move to B2, right? And that caused a collision. So, according to the algorithm, it says that if there's a collision at state t plus 1, or step t plus 1, you ignore that state, move back one step, consider all possible states that do not cause collisions, and choose the one that minimizes global cost. Move the robots and repeat. So this is where the important key concepts are going to come in, or key terms for the algorithm. So first, we identified a collision, right? That in the paper is going to populate something called a collision set, which is going to be a set of states for both robots that identify when they are going to collide. That way you can never consider them again. In this case, that's B2, B2. Can anyone see that? I mean, it makes sense more or less because it's collision set of collisions, right? But anyways, the next important concept is that whenever you do collide, you need to consider every other possible move, right? That in the paper is called the backpropagation set, and that's important for the P set. The backpropagation set is literally every possible move that does not include the collision. Does that make sense? So I won't sit here and bore you writing down all possibilities, because if you look at it, there's 20 minus 1, 19 positions that you could possibly take from here, right? Instead, I'll show you the top 3. These are the top 3 choices for moves, right? You calculate the global cost by using some heuristic, and let's say that these are the 3 costs. So if you're trying to minimize the global cost, which one would you choose? Which action, if you can see the costs? Right, so for the blue robot to move up and the red robot to stay in its place, it costs 5 globally. For the blue robot to stay and the red robot to move down, it costs 8. And all the way over there, for the blue robot to move up and the red robot to move left, it costs 15. Right? So you choose this action to minimize the global cost. So once you move, you keep repeating the algorithm. You move the robot to the right, the blue robot to the right, you move the red robot down. There's no collisions, right? You keep going, and the robots eventually make it to their state, or their goal. Does that make sense to everyone? Yeah. Alright, so brief recap one more time. This is the overall step-by-step thing that you do. You follow the policy to the collision. If there's a collision at state 1, at step t plus 1, move back one step. You populate the collision set with that collision. You consider all possible states that don't cause a collision, also called the backpropagation set. You move the robots and you repeat. Yeah? Alright, so before I pass it on to the network flow, I'm going to ask you one extension for this. So let's say that there are 3 agents, or any number of agents. Let's just say 3, to make it simple. The third agent is moving along, and when there's a collision, it's not involved in it. What do you think that the third agent would do following this algorithm? Anyone have any ideas? No. Well, if you follow along, right, if two agents are colliding, then you have to consider all these possibilities to avoid the collision, right? If it's not, you just follow the policy. So in the case of more agents, if there are any agents that aren't involved in the collision, they simply follow their policy all the way along until they do collide. And that's it. Does that make sense? Perfect. So I'll pass it on to Yui talking about network flow.
So hi everyone, my name is Yui. I'm going to present another approach that I will help you to tackle this problem, the multi-agent path planning problem. And the third approach is called network flow. So we get the idea from the research paper called multi-agent path planning and network flow by Yu. And we also bring some example and description from the textbook written by Professor Michael Sipser about theory of computation. And Professor Sipser is at MIT. So does anyone take theory of computation course with Professor Michael Sipser before? Okay, so if you take it, I'm sure that you will be like a bit familiar with this technique. It's a technique called reducibility. So it's the way that we convert one problem to another problem. So let's say we have problem A and then we convert it into problem B. And if we can find a solution to problem B, we can use that same solution to solve problem A as well. Actually, you might not be aware that you might use reduction in your daily life problem. For example, if you travel to a new city and you want to find a way around the city, you might reduce the problem to like obtain a city map. Because if you have a map, then you know like where each place is located and how can you go from one place to another place. Another example is like if you want to travel from Boston to Paris, you might reduce the problem to finding a plane ticket between Boston to Paris. So is there anyone have another idea about reducing this problem, traveling from Boston to Paris? Okay, so actually one of my friends, he suggests me like that like I can reduce it to be like easier problem. Let's say if you have a boyfriend, you just like ask him to go with you so that he will like do everything for you. But yeah, I mean, but if you don't have a boyfriend, maybe you need to first like find one. And I don't know, maybe whether it will be like become a harder problem or not. Okay, so back into our example. So like we are talking about multi-agent path planning problem, and we can also reduce it to network flow problem. And I'm going to tell you about like how network flow problem look like. So okay, so let's say we have two types of commodity, the blue one and the red one. And we have the like 6 nodes, which means that it represents each stop that like the commodity can be like travel to. And let's say we have a truck that like move from one node to another node. And each represents the road that the truck can be travel through. So from node 1, we have 10 units of blue commodity, so we call it the supply node. And we want to deliver this blue commodity to the second node, which is the demand node. And you can see the negative side of -10. It means that we want 10 units of blue commodity to be like delivered here. And in the same way for the red commodity, like the supply node for the red one is at the 5th node, and for 20 units of supply. And we want to deliver it to the 6th node. That, okay, we want like 20 units to be arrived here. And for each link, I mean the road that connect each node, there will be two properties attached, the cost and the capacity. You can think of the cost in terms of the time you need to take to travel from one node to another node. So let's say you have like longer road, like 5 kilometers, then you might make like 5 times step to go there. And I denoted by like longer link to represent like higher cost. And for the capacity is like how big the road is. So like the bigger the capacity, it means like more truck or like more commodity can be delivered like at 2 times step. So you can see like the capacity of 30 have like the thicker arrow than like the capacity of 10. Okay, and because like we have the goal to deliver these 2 commodity, and we can also like maybe minimize some of the attributes. For example, we want to like minimize the cost that we need to spend. So we can then formulate this problem into the optimization problem. Let's say we want to minimize the total cost, and there are three constraints that we have to take into account. The first one is the capacity. It means that you cannot exceed the capacity of each link. And the next one is the balance. So the commodity that leaving the supply node have to be balanced with the commodity that entering the demand node. And the last one is you have to make sure that the commodity that travel through each link is positive. Because if it becomes negative, then your solution will not be the correct one. And okay, then so because we formulate that problem as the mathematical programming, you can use any existing integer programming solver to solve this problem. And as you can see, the solution is we travel from node 1 to node 2 and carry 10 units of root commodity. But for the red one, we have to divide it into two roots, because even though the link from node 5 to node 6, it can accommodate all 20 units of red commodity, but the cost is so high. It's like the cost of 5 per for each unit of the commodity you have to transport through. So that's why we split it into two lines here. And actually, this problem we can make it to become the multi-agent path planning problem, and how to serve. Let's say we change each commodity to be the agent or the robot. So then you can think about the agent to have the supply of 1 unit. And then we also have the demand, which is the goal node of each agent, and the demand will be -1. And we also have to make sure that each link have the cost of 1, and also the capacity of 1. The capacity of 1, it means that only 1 robot can be traveled to that link. And the cost of 1, it means that we make some assumption that each robot have the same speed. So it take only one time step to move from one node to another node. So, but actually you might feel that this problem is unsolvable, because we only have 1 link from 3 to 4. But the robot one and the blue robot and red robot should be able to reuse that link in different time steps. So, for example, it should be possible to for the blue robot to start to move at time step 0, and the red robot to start to move at time 1. But because we want to incorporate this we want to solve this restriction, and also for this network flow problem, you might notice that it is the directed edge. But actually, robot can move up or down or left to right. And then Sung Kwon, he's going to present how can we make some more details to tackle this property.
Okay, so far you gave some intuition about this approach and also explained about the network flow problem. So from now on, I will explain how to convert our multi-agent path planning problem to the network flow problem. And before that, let's give some of the assumptions of our problem first. So with this approach, we are going to find the robot's collision-free path based on the graph. And all of the edges of the graph should have the same distance. And the angle between a pair of 2 edges should be greater or equal to 90 degrees. And we will also assume that all of the robots have the same speed. Actually, this kind of grid map is one of the possible options for our problem, but it's not the only one, and I will give some example about that at the end of the presentation. So here is our simple example, and in this example, this robot should go from here to that node, and this robot should go from here to this node to charge their battery. So this is a really, really simple example, but we cannot simply apply the network flow problem formulation directly because of several problems. First of all, all of the edges here are not directed ones, but where all of the edges in the network flow problem are directed ones. So in other words, robots should be able to go back and forth in the graph of this kind of problem, but the directed edges of the network flow problem cannot support that. And second of all, there is no notion of time in the network flow problem. So in other words, the solution of the network flow problem is assignment of the edges from the initial location to the goal location without considering when it uses each link. But as you can expect, we need some kind of notion of time or sequence to keep track of robot's movement for each time step. So to convert our problem to the network flow problem, we have to expand our original graph through time by adding some directed edges. And let's do that step by step together. So this is our original graph, which is rotated and distorted a little bit for the visualization purpose. And let's say this is a snapshot of the graph at time step t. And also for the explanation purpose, let's focus on this single edge, which connects the node A and node B. And let's draw a copy of this graph. And this is a snapshot of the graph at time step t plus 1. And I also added the real-world map for the reference purpose. So the first thing I want to do is to model this kind of movement, which is going from node A to node B. So can anyone suggest how can I add some directed edge here to model this kind of movement from node A to node B? Okay. So we will add this kind of edge here like this to model the movement from node A to node B from time step t to time step t plus 1. So the one thing you really have to calculate is that this red edge is not the real world edge, and the meaning of this edge is traveling in time from time step t to time step t plus 1 from node A to node B. And similarly, we need to add this green edge to model the movement from node B to node A from time step t to time step t plus 1. And we also have to model the stationary actions because some robot may want to stay at the same node for subsequent time steps for some reasons. And that can be done by adding these edges like these blue ones in the slide. And now this whole gadget here is quite looks like network flow problem. So let's focus on this whole gadget here. And as you were seeing in the previous slide, these red and green edges are for the movement for the opposite direction. So we have to make sure that only one path is used for this time step. But for this configuration of the graph, we cannot do that. So we have to modify the graph like this. So what I did here is that I divided each red and green edges as 3 pieces, and I merged the middle parts. And I also assigned the capacity 1 for each part. So then since only one path can be used for this time step, there will be no collision. And also since each path here is for the single movement, we have to assign cost 1 for each entire path. And that can be done by assigning cost 1 for the middle part, but 0 for the other paths. And it will be obvious that the cost and capacity of the stationary action should be 1. And now it is really exactly the small size of the network flow problem, and seems like we're almost done, but not yet. So does anyone have an idea what kind of collision can still occur with this kind of graph here? So you cannot solve all of the conflicts, so there can be another conflict, not because of the opposite direction. So yeah, the answer is this kind of situation can still occur. So if one robot goes from node B to node A, and if the other robot stays at node A, then there is collision, but this graph cannot prevent that. So to fix that problem, we can add additional directed edges, like these yellow ones in the slide, and assign capacity 1 for those yellow edges. Then since only one robot can be at each node at the end of this graph, we can prevent the previous situation. So until now, we have done this. Actually, this is the same graph, but I distributed a little bit more. So it's exactly the same thing as this one. So until now, we have done this for a single edge. And we will do the same thing for the other edges like this. And if we do this for each time step from 0 to some fixed time horizon t, then we can get the big size of network flow problem, which can be solved at once. So now I will give some general overview of the procedures. So starting from the original graph, copy the graph for the next time step, and connect them each other by adding directed edges, as explained before. And repeat it until some fixed time horizon t. Then finally add initial and goal states, and just forget about the original graph. Then finally we get the pure network flow problem, which can solve equivalent communication path planning problem. So this is one of the solved example based on the grid map. So as you can see in this example, all of the robots goes from their initial node to goal node without any conflict. So as I mentioned in the earlier this part, actually this kind of grid map is not the only one that the network flow problem can solve. So if we couple some roadmap algorithm with this algorithm, we can tackle more practical situations. So here there are two kinds of obstacles and goal regions. And if we make the map with some roadmap algorithm, then we can simply apply the network flow approach to them. So as you can see here, one robot waits for him. And when they approach each other, actually these two and this one can collide each other. So this one will be for this one and go together without falling. So this is the end of the network flow part, and I will finish the lecture by giving some summaries of these three algorithms. For conflict-based search, basically conflict-based search solve the relaxed problem without considering any conflicts. And if it detects some collision, then it adds some artificial obstacle at that collision point, and keep solving the problem again and again. And for the efficiency, it uses some concept of constraint tree to keep track of the collisions. And MSTAR is quite similar to CDS approach, and it also solves the problem. It also solves the relaxed problem. And when it detects the collision, then it grants the solution based on the policies and some collision set or backpropagation set functions. So both MSTAR and CDS share the concept of branching and conflict detection, but they use different kinds of schemes for their branching. So because of this, one algorithm can be better than the other for some specific problem instance. So based on our experiments, basically CDS is much better than the MSTAR when there is less agent and when there is less conflict. But MSTAR is better when there are much of multi-agent and there are much of conflicts. But it's very difficult to say which one is superior than the other. And network flow approach is quite different from those two previous approaches. It just converts the original multi-agent test plane problem to pure optimization problem, so that we can use the techniques and traits that were developed for the optimization problem. So for example, there is a class of the multi-agent test plane problem, which is permutation invariant multi-agent test plane problem. And for that approach, we can simply apply the linear programming approach, which is really efficient and fast to solve. Yeah, this is the end of the presentation, and please give me questions.
About network flow, do you have any concept of the computational time it takes to actually build the network flow graph as opposed to compared to solving the problem. You can imagine if you have a large branching graph, actually building the graph could take some time.
Actually, building the graph is not that computationally hard, but actually solving part is difficult. Actually, yeah, the building part is really simple. Yeah, and actually solving part is just optimization problem. So if we have to solve the not permutation, not invariant problem, then that can be solved with integer programming. So we can use the tricks of the integer programming approach, but it's still integer programming, so it's a little bit computational. Yeah, if you don't have any questions, we prepare the presets, so we can introduce the presets here.
Just a quick question before we introduce the preset. For the preset, we have implemented actually all the algorithms, and we created a small preset for network flow, one for CBS and one for MStar. And we haven't really decided on which one we should give you guys yet, because we're not going to make you guys implement all of them. So before we start showing parts, maybe you want to think about it by when we go to the preset, which one do you actually want to implement at the end, because we haven't decided, and we're going to decide after the lecture. So yeah, please pay a little attention and see what's maybe the easiest or the hardest, depending on your preference.
We haven't, as Sandra said, we haven't compiled the three implementations into one Jupyter notebook, but we have all three here, so we can go through each one of them. So, so this is the CBX one. You will basically go through the same problem we talked in class, step by step, and there won't be a huge amount of coding you need to do, but eventually you will arrive at the situation where you can resolve the conflicts by comparing the solutions. And yes, and again you have two written answer problem where you have to find an algorithm that probably similar to the CBS, and also one final thoughts problem where basically you share your understanding of the problem. And now we're going through. Any question for this? It should be very straightforward. If you take a look. Yeah. I'm a nice person, so I don't have hard problem. Network flow. Yeah.
So for the network flow preset, we plan to want to implement three functions. So for this one, let's say you have the original CUG, one edge of original CUG. So let's say U and V, and you have to expand the gadget as Sungkwon present. Like from one link of CUG, you have to expand into 5 links, and you have to follow the node name annotation here. We also provide a test function for you, so that you can take a look whether which part is incorrect. And then, okay, so for the first part, you have only one link of CUG, but now we provide 3 links and 3 nodes, a true link with 3 nodes, A, B, and C. And you want to go from the start node A to the goal node C. And for this problem, you have to add the green and the blue edge here to represent the time expanded graph. In this case. Yeah. Finally, you have to set all the terminal because let's say it's okay, because we have to somehow tell which node is the start node and which node is the goal node by using the value of demand. So you set the demand to 1 for the start node and set the demand to -1 for the goal node. Oh, actually we have 4. And for for the last one, you just like put all three functions all together, and then you can like get the full expanded CUG function, so that it becomes the full network flow that you can like submit to the solver for solving for the solution. And like the rest of this preset is for you to like play with the animation and simulation. You can adjust the dimension of the CUG grid, and also like adjust the number of agents. You provide a function to make the CUG grid here. Yeah, you can change the n and m value to like represent. For example, this one we have 5 by 5 grid. Okay, we also provide a random function for you to like specify the number of agents you have, and if you random initial node and goal node. And we also provide a simulation function for you to like see how your expanded CUG will look like. Yeah, like for this case, is how, I mean, if you adjust the n and m, the CUG parameter to be smaller, then you can see like a bit clearer, like simulation. Because and then we make use of the built-in solver provided by Network X package. So you just submit your time expanded graph here, and then you get the flow and the flow dictionary and the full plots. And we also provide a return path function for you, so that you can extract how the path will look like. And then given this path, you can submit to our provided simulation function. So it's like it will be a simulation that like it will play for how the robot can move from the start node to the goal node. Yeah, like this one. Yeah.
Yeah, for the subdimensional expansion in the MStar preset, we're basically gonna make you guys implement two functions. Miguel talked about the back propagations function. Oh, this is the scenario. We actually want to get those robots to the safe zone. That's what it's all about. And we're gonna make you guys implement the back propagation function, which is that's the answer, so you don't want to look at that one. Which is a pretty straightforward function, I think. And we provided pseudocode for all the functions as well, so it should be pretty much like the IRA piece, if you recall. Not too hard, I think. And also we're gonna make you guys use the back propagation function to create finish up the implementation of MStar. And as you can probably see from this pseudocode, MStar is pretty similar to A-star, so it shouldn't be too bad if you implement A-star before, actually. And here's an answer here as well. Then you're gonna, of course, test it, and then as you saw with the other network flow algorithm, the one thing is actually implementing function, but when you do multi-agent planning, I think the most fun part is actually visualizing the results. And by the end of both now all these algorithms, you're gonna be able to actually see how it looks like in the end, and you're gonna in Amsterdam want to create something like this, which is an animation of how the robots will eventually move in the network once you have hopefully implemented the right one. And I think it's like really important when you do the PSAT. Yeah, you finish the code and everything, but you actually want to in the end run our code that we have provided to visualize the results, because it just puts like the whole thing together really. And I think that's actually it. We're going to combine. We're going to decide on which one of these algorithms to make you guys actually implement. We might make you guys implement part of the other algorithms, but we're probably going to provide a good part of the implementation of MStar and CBS and network flow. We'll see. But the goal is that by the end, you guys are going to run all the algorithms and try to like visualize the result and see how the algorithms compare, like when you run with a certain amount of grid and you increase the agents, and you see really what algorithms are the most efficient ones. That's our goal for the very end, and that should be the PSAT in short.
A brief notice, I implement my code in Python 2, and those guys are in Python 3. You may probably not be able to compare the CBS with the other two, but you certainly will have a result comparison with network flow and IMStar.
And that should be it. Thank you.